I'm ready to give the 25-minute talk about high-resolution brain imaging, mobile brain-body imaging, and other concepts and technologies we're developing here. But I think because of time, I will just abbreviate this talk. And that was the first EEG lab in the US. I think it was at Harvard in the 30s. It's come a long way. So in 2001, we got the opportunity to form the Swartz Center because of the work of the good work of development at UCSD and the connection of Terry Sinofsky with Jerry Schwartz, the founder of barcode laser reading technologies. So this was the message. This was the vision message that I put on the Swartz Center. The goal of the Swartz Center is to observe and model how functional activities in multiple brain areas interact dynamically to support human awareness, interaction, and creativity. And that's what we've tried to do to develop computational techniques that allow us to approach those goals, us and others doing the research to approach those goals. Now, no one's mentioned money here before, but I will. So the Swartz Center began with a $6 million gift letter to UCSD, which was to be doled out monthly at a rate of $800K a year. It was essential for us to do exploratory work and to develop a center off campus at that time on Regents Road that could never have been funded by piecemeal by NIH, the rigorous process of getting NIH grants. Through the Office of Development, that gift letter was increased to $12 million in 2003. And our work continued until 2010 when this new building became available and this floor was given to INC. At the same time, the Swartz Foundation funding itself ran into some problems because of the crash. And so they reduced the amount per year to $360K. And as per the gift letter, that should run until June of 25, which would make us a continuous 24-year grant. Quite extraordinary and quite immensely useful within the university context because it's money that can be used for pilot projects for people who don't yet have funding and for exploratory development. That's in a way that's very difficult to fund in any other way. So the Eeg technology itself has developed over the years largely because of the availability of computer technology. Here was in '97 where you could now make a movie of the actual electric field on the head. And now we're hoping and we're working hard on creating a high-resolution EEG imaging. The secret of our progress, I think, is that we've always been guided by the idea of, well, what is EEG actually? We know it's small part of brain electrical activity that gets out to the scalp. But what part? How is it triggered? How is it modulated? It's continuously changing. And what is the functional significance? And if you don't ask from that biological point of view those questions, then you cannot build the computational techniques that are appropriate for understanding what information is actually contained in the EEG data for use in your brain research projects. Now I'm going to skip through lots of interesting things, including about our EEG lab environment. We're best known around the world for that. The 10,000th citation to EEG lab, the EEG lab paper, is going to happen on Wednesday in Google Scholar. Because they're increasing at 4 a day and they only have 6 to go. So there's about at least 3,000 sessions started every day of EEG lab around the world. We're now collaborating with the Supercomputer Center, so now you can use, as a nonprofit researcher, you can use free supercomputer time. You can run intense EEG processing jobs using EEG Lab on the Exceed network of supercomputers, including the Comet here. And under a proposal that's now pending, but pre-approved by NIH, we hope, that will turn out to be the case, This facility and our collaboration with Dr. Majumdar at the Supercomputer Center will turn into the portal to the National Brain Imaging Database, which is begun at Stanford by fMRI scientists, and we would provide the EEG portal. The development of large, well-documented data archives makes it possible to apply all the revolution in artificial intelligence, machine learning, and big data approaches to the brain activity and extract more of that wonderful information that is contained in these recordings and has been for decades, but without the methods to get out. Well, this is about EEG Lab. This is about some of the technologies we've developed that are contributing to it. Here's some of our collaborators on campus and elsewhere who do clinical research but haven't been able to extract much information from their EEG relative to the amount of information that potentially is there in the data that we've been working with Greg Light in schizophrenia, with Sandy Liu at UCLA on ADHD, and my own interest has been in affective neuroscience. So with Julie Onton, now an INC project scientist working on PTSD, we studied the brain dynamics supporting emotional experience in the form of imagined emotional experiences with a careful paradigm. What we found was you could tell how good or bad, exactly how good or bad the feeling was that the subject was experiencing, sitting with their eyes closed, by the high frequency activity in two small portions of the cortex. Later we found studies have confirmed that with fMRI, but it was found with EEG first. And I look forward to the day when we can study the most subtle and personal interactions, social interactions, and experiences of our lives. And this is a mother and her adult child in a psychotherapy session. We can study the brain dynamics moment to moment in those settings. It's technically possible. It just needs imagination, and that requires the funders to have imagination as well. We've turned our attention also to studying brain dynamics during natural behaviors. Ballet dancing may be a little difficult, but instead of lying in a scanner and fixating your eyes, we can now, you will see the Moby Lab, and you can see that we can study brain dynamics during motion. And we've developed the acronym MOBI to describe this new imaging approach. Here's an example of it applied to a juggler. So there's one of our postdocs juggling. And on the left, you see the interactions between brain centers that appear in the EEG and give us clues about how the brain is organizing the behavior to optimize its outcome. In other words, to keep the balls in the air. Here is a former graduate student, Grace Leslie, now a professor at Georgia Tech, who wanted to study emotional expression in music and the experience of music. And so this is he's deaf.
Not like that. Can you really hear?
And she's trying to communicate to him what the music is feeling is. See? So in the lab, we created the same paradigm. This is our programmer trying to express music, maybe not quite as well. But the result of that we published was a beautiful result. There was one spot in the brain, of course, many things were happening in the brain to support this behavior, but there was one spot that had to do with the emotional communication, the feeling that you're trying to express to someone, even if in this case it was an imaginary person, but trying to express to someone what you're feeling, what the music feels like. And this turns out to be the place in the brain that's known from fMRI studies and others to be associated with emotional control, with hand control, and with active thinking about the feelings of another person. John talked a little about our work with music. Both John and I have music backgrounds, and so a couple of years ago, or a few years ago, we won an award from the UC president and created a research community of scientists across the UC campuses. We had symposia and meetings. We funded cross-campus pilot student research and pilot research among faculty. And I believe the science of music and music in the brain is a highly fundable effort. If there is a donor who would be inspired, both John and I would be very happy to, and others on campus would be very happy to speak. So this is the beginning of an era of functional imaging. Brain-machine interfaces, you'll see. Mobile brain-body imaging, imaging of natural cognition in action, and what I might call brain AI. Big data, biomarkers, looking at the landscape of individual differences, looking at customized approaches to treatment for a whole range of psychiatric and perhaps other conditions. So it's really a very exciting time after my 30 or so, 35 years in EEG research. This is really the time where it's beginning to, I think, bear fruit. And the next 20 years will be very exciting. Thank you.